Alright, so this video is all about eccentricity, which is a measure of how circular a shape or a curve is. And so an interesting thing right before we start is the word eccentric, right? The conics will range from circular, the most circular being a circle, to eccentric, which are like hyperbolas, which are nothing like circles. And what's really interesting to me is that the word eccentric itself means out of center, right? That's what it originally meant, and now it kind of means like most people think crazy, right, when they hear eccentric. But in this context, it really just means out of the center. Like an early example is like an elliptical orbit, or in something that doesn't orbit right around a center, like how an ellipse, it's around those two foci, rather than an exact center like a circle. And then as it gets more and more eccentric, it just gets more and more out of the center, and less like a circle, which I thought is really cool. Anyways, moving on. So when things with eccentricity of 0, that's a circle. If E is 0, then it will look exactly like a circle. And I don't want to draw a circle. I feel like that'll just, let's see if I can get a shape. That'll just be embarrassing. But it will be a circle. Oh my god. Like this. See? Pretend this is a perfect circle. That is something with eccentricity of 0. Next, if we have eccentricity that's less than 1, but more than 0, that will be an ellipse. Okay, so ellipses always have some sort of eccentricity between 0 and 1. And let me just copy this, paste it again, and stretch it out. Look at this. This thing right here is similar to a circle, right? It's very close, but it isn't 0, right? Just because it's not a perfect circle. Next, we have things with eccentricity of 1. So let me write circle, ellipse, and that would be a parabola. Parabolas have eccentricity of 1. Pretend that is a normal parabola. And so those things, they always have eccentricity of 1, which is why sometimes when they ask you to like identify a conic and you can easily find eccentricity, just find the eccentricity, because if it's 1, well then you know it's a parabola. And then finally, if the eccentricity is greater than 1, it is a hyperbola. Right? And so this is definitely nothing like a circle. I mean, even a parabola, oh my god, I cannot draw. But even a parabola, I'd say, is nothing like a circle. But at least, it kind of curves in one direction. But hyperbolas, they're curving in 2 directions. Like, it would look more like a circle if you flip these sides around. And even then, of course, it would look nothing like a circle. So what I'm trying to say is, these are very eccentric. They're nothing like circles. And so, the greater the eccentricity gets, the less like a circle it is. Okay, so what are some ways that you can calculate eccentricity? Well, my favorite way to think about eccentricity, the numerical value, is it's the distance from any point P to the focus of the conic over the distance from any point P to the directrix. So this kind of explains why the eccentricity of a circle, or you can think of it as C over A, where C is the distance, I trust you know from standard form, where C is the distance from the center to the focus, and A is the distance from the center to a vertex. And this is what I was going to say before. This kind of explains why the eccentricity of a circle is 0, because a circle has one focus. And it's right at the center. So the distance from the center to the focus is just the distance from the center to the center, which is 0. So no matter what A is, the eccentricity of a circle will always be 0. So that is why circles have eccentricity 0, and C over A is the most common used way to calculate eccentricity, especially in equations that don't look super funky or weird or something. Way 3 is this. Sometimes you'll see conics in polar form where they'll have numbers, and they'll have some trig function on the bottom. If they ask you to find eccentricity, you probably want to get it into a form that looks like this, and then you can easily calculate eccentricity. And I'll show you examples of all of these. So let's start with c over a, because that's pretty common. And I trust you guys know how to put conics into standard form of, of like ellipses, of hyperbolas, or whatever their respective standard forms. So like, let's say, let me just make something up. Let's say we have a conic x minus 5 squared, and this is in our standard form. It's going to be an ellipse, okay, over 9 plus y minus 3 squared over 4 equals 1. Well, for an ellipse, a squared minus b squared is equal to c squared. And I hope you guys remember that since the standard form is x minus h squared over a squared, or whatever, a squared or b squared, this is for a horizontal ellipse. This is the standard form. Plus, this is, a squared is 9, so a is 3. B squared is 4, so b is 2. And so I guess we don't really need that, because a squared minus b squared is 9 minus 4 equals c squared. And so c is going to be the square root of 5. And now we have a is 3, so the eccentricity is square root of 5 over 3. And you would do the same thing for hyperbolas, except for, a hyperbola, a squared plus b squared is equal to c squared in the hyperbola. That's the one difference in an ellipse and a hyperbola. But I'm sure you've seen this before. I really, really hope this is a review, and if it isn't, please, you need to learn this. So I'm just going to move on, but that's how we use method 2, right, to calculate eccentricity. And then now let's look at 3, because that's also pretty simple, and I have a very extensive example for 1, which I like a lot. So let's look at 3 next. Sometimes you'll see polars used to represent conics. So if you have something like r equals 5 over 3 minus cosine theta. Oh, let's do 3 minus 3 cosine theta, okay? Well, we want to get this into this form, and that will really help us get our eccentricity. So, what we can do is the rest of this is kind of variable, right? But the things that aren't variable are this 1 and this cosine, okay? Cosine is today, which shouldn't be hard, but this 3, we have to figure out how to turn it into a 1. So the easiest way to do that is let's just divide both the top and the bottom by 3. So this gives us 5 over 3 on the top, and then 3 over 3 on the bottom, which is just 1, minus 3 over 3, which is 1, cosine theta. Now, looking at this right here, we should have 1 plus or minus e cosine theta. And so, because we have 1 here and 1 here, it tells us that e is equal to 1. Another thing is that if e is 1, then this also can tell us the direction of the directrix and how far the directrix is from the center. So and by center, I mean the origin. It's called the pole in polars, so it'll tell us how many units it is away from the pole. So if E is 1 and ED is 5/3, well then D must be 5/3 for the top to work out. And so what this tells us is if we have a conic, and this is the pole, right? This is the polar axis, this is the pole. The eccentricity is 1, so it's going to be a parabola. And the directrix is going to be 5/3 units. And then since this is cosine, cosine deals with left or right. And since this is negative, it's going to be left. So the directrix is going to be 5/3 units left of the pole. So this distance right here is going to be 5/3. And so since it's a parabola, because the eccentricity is 1, it's going to look something like this. Okay, so we can tell so much just by manipulating that polar equation just a little bit. And I think that's pretty cool. Okay, so let's do just one more example, and this time we'll use sine. So let's say r equals 10, let's say 4 plus 3 sine theta. Okay? Now we manipulate this by dividing both the numerator and denominator by 4, and we get 10/4, so 5/2 over 1 plus 3/4 sine theta. Well, we know that we have this in 1, so the eccentricity is just the number in front of sine in this case. So the eccentricity is 3/4. And then we know that ED is 5/2, but E is 3/4. So 3/4 times D is going to equal 5/2, which means D is equal to 20/6, or in other words, 10/3. Okay? And so this means, especially since, eccentricity is 3/4, which is in between 0 and 1, so this is an ellipse. So this means one of the directrixes, plural directrix, one of them is, this means the plus, okay? The plus, since sine deals with up or down, the plus means it's above the pole. So one of them is going to be 10/3. So this distance is 10/3 above the pole. And then the eccentricity is 3/4, so it's going to be an ellipse. So that's how we'd use this formula to find eccentricity. Okay, moving on. This is, I think, the biggest way to find eccentricity that actually deals with what it is. And this is very versatile. It's the distance from a point to the focus over the distance from the same point to the directrix. So let's take a look at this question, okay? So this is from some mu alpha theta analytic geometry test. I don't remember which one. Please don't sue me, mu alpha theta, but it's from one of those tests. So it says a conic section contains the point 1, 3 and has a focus at -2, -1 with its corresponding directrix at y = 5. And then it asks for the eccentricity. And so we know that if the conic section has the point 1/3, we need to find the distance from that to the focus. This is a really nice question. It gives us all the information that we need. So the distance from P to the focus can be easily found using distance formula. Right, so that's just the distance equals the square root of x2 minus x1. So -2 minus 1 is -3 squared plus y2 minus y1. So -1 minus 3. So -4 squared. Basically, we're doing Pythagorean theorem with the distances, right? We're going from 1 to -2, which is the distance of 3, plus 3 to -1, which is the distance of 4, and we're squaring it, and wow, this is a Pythagorean triple. This is the square root of 9 plus 16 is the square root of 25, which is 5. Okay, so the distance from the point to the focus is 5. Now we need to find the distance from the point to the directrix. So now we think if this point is at 1, 3, and the directrix is at y = 5. So this is y = 5. This perpendicular, remember the shortest distance from a point to a line is the perpendicular distance. So this point right here is going to be 1, 5. And the distance from these two, this forms a right angle, is just going to be 2. So the distance from the focus is 5, the distance from the directrix is 2, and therefore the eccentricity is going to be 5/2. Yay! Okay, so at this point you might be thinking, this isn't bad at all. And I agree, it isn't. But it's about to get a lot funner. So now we want to get the equation of the conic section, okay? And all we're given are 2 points and the equation of a line. And it's just so cool to me that this is possible. Like, we can get the equation of the entire conic section using just 2 points and a line. Like, okay, I will stop talking and just explain. So we know that the distance from any point on this conic section to the focus, the ratio of that to the distance from that same point to the directrix is going to be 5/2. So we can make a little ratio for this. And so we can say, using the distance formula, for any arbitrary point x, y, and let me write the actual, let's write all of our information here. So what were our points again? They were 1, 3, focus is -2, -1, and the directrix is y equals 5. Okay, perfect. So now we know that for any arbitrary point xy, the distance to the focus is going to be the square root of the distance from x to the, we're using this distance formula again for this. So x minus -2 squared plus y minus -1 squared, right? Just distance formula. And then the distance from the point y to the line is just going to be the absolute value of y minus 5, okay? Because it's just, we're just doing the difference, right, between y and this y, which is 5. Like, imagine just a number line from any point y to 5. The distance is just going to be the absolute value of y minus 5. And so we know that this is equal to 5/2 because that's our eccentricity, the ratio of the distance from any point to the focus over the distance from that point to the directrix. And so let me just simplify this a little bit. So instead of having our double negatives here, we can just have 1 positive plus 2 squared plus 1. Okay, perfect. And so we're going to cross multiply and just algebra this out. So does we get 2 times the square root of x plus 2 squared plus y plus 1 squared equals 5 times the absolute value of y minus 5. Okay, so now that we've cross multiplied, we want to get rid of that radical by squaring all of this. So we get 4 times, let me just expand all of this out, but we're just going to square this and there's going to be no radical. So we have x squared plus 4x plus 4 plus y squared plus 2y plus 1 equals 25 times y squared minus 10y plus 25. Okay, now we're going to expand both sides out, and we get 4x squared, should be a plus 16x plus 16 plus 4y squared plus 8y plus 4 equals 25y squared minus 250y plus 625. Jesus. Okay. And now we want to get all these to one side. And as you can see, this is looking pretty nice. Can you believe that we turned our 2 points and a line into this? Because once we combine like terms and get it all to one side, this will look a lot like the general form, right? It'll look like ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, right? That is our general form, and that is the form we want to get this into as our equation for this conic. Okay, deep breaths. Let's combine like terms. So 4x squared. Are there any other x squared terms? No. So we have 4x squared. Now let's look for any xy terms. Are there any? No. Let's look for cy terms. So 4y squared and 25y squared. So 4 minus 25 is -21y squared. Let's look for x terms. We have 16x over here and no other x terms. So plus 16x. Let's look for y terms. We have 8y and we have -250y. Wow. Okay, so we add 250y to both sides and get plus 258y. And so now we just have our constant. So that's 16 and 4, which is 20. And then 625. So 20 minus 625 is -605 equals 0. So this should be the equation of our conic section. Okay, good job. We did it. Hopefully this kind of showed to you how cool eccentricity is, how useful, how practical. And you should practice this a lot because this is something that you'll see once and you'll be like, oh, I get it. But, you know, most of the times if you look at this once and then you get a question like, oh, here are some 2 points in a line and write an equation of a conic, you're going to be like, what? So practice this a lot. But hopefully this was helpful.